Already we know that for an NMR spectroscopy, a nuclei should have I is equal to half, and among these one of the important nuclei is the 1H1, that is a proton. And another nuclei which is again used in the NMR spectroscopy is the 6C13, which is an isotope of the carbon. Now 1H1 is called proton NMR and 6C13 is called as carbon NMR, or sometimes it's also called as CMR, carbon magnetic resonance spectroscopy. In both of these spectra, one of the important aspect is the spectral interpretation. How we can get the information of a structure by seeing the NMR spectra. So in this video, let us see how we can get the interpretation of the NMR spectra and what are the rules governing these. So let's start. NMR spectral rules. So in order to define the NMR spectral rules, first of all we have to define first order NMR spectra. What is the first order NMR spectra? That is the ideal condition we have to achieve in order to observe the NMR spectral rules. So first order NMR spectra is the spectra where the chemical shift delta nu is greater and greater than coupling constant J. So delta nu is greater and greater than J, then it's called first order spectra. But what is this chemical shift and what is the coupling constant? Now let us see simply what is a chemical shift and coupling constant. Suppose this is an NMR spectra and this is a standard peak and this is a sample peak, and the distance between these two spectra is called as the chemical shift. So chemical shift is the delta nu, which is the shift of the peak from the standard reference peak. And this type of spectra is observed under low resolution. So this is called low resolution spectra. But if we apply a high resolution like a zooming, under the high resolution spectra we can observe the same spectra as like this. So now this is the standard peak, but the sample peak A can be observed as a two splitted peaks. That means a single peak now is observed as a two splitted peaks, and the distance between these two peaks is very small compared with the chemical shift. And the distance between these splitted peaks is now called as the coupling constant G. So we can easily observe that the chemical shift delta nu is very greater compared with the coupling constant. So that type of spectra is called first order spectra. So in the first order spectra, delta nu is greater and greater than J. Now when this NMR spectra follow this phenomena, then we can apply few of the rules in order to interpret the NMR spectra. So let us go with the different rules in the NMR spectral interpretation. So let us start with the rule 1. All magnetically equivalent nuclei will give one NMR signal. So in order to understand this rule 1, we have to define what is the chemical equivalence and magnetic equivalence. Suppose we have a structure like this and we can observe the protons here. This is one type of proton, this is another proton, and this is another proton. And here all these three protons are connected in a similar way to the carbon, so they are chemically equivalent. So chemical equivalence is the equivalence in the linkage. So here all these three protons are equally connected, so they are chemically equivalent. And since they are connected to the carbon, which is sp3 hybridized, so they are having the tetrahedral structure and they are oriented in a similar way, so they are magnetically also equivalent. So magnetic equivalence is the equivalence in their arrangement within the space. So here these protons are equivalent, they can be indicated by letter A, and these protons are chemically as well as magnetically equivalent. But if you see the other types of protons, here the chlorine is attached. Because of presence of chlorine, this proton is different from the proton A. So now this proton can be indicated by letter B, which is chemically not equivalent, because this proton is attached with the carbon, which is attached with the chlorine. So now this is chemically not equivalent, therefore magnetically also not equivalent. And here we can also observe another proton which is equivalent to the proton B. So now in this compound we have the two types of non-equivalent protons which are indicated by letters A and B. So chemical equivalence is the equivalence in the linkage, and magnetic equivalence is the equivalence in the configuration or arrangement within the space. Now let us take another example here. This is an alkene. Now in this alkene we can observe this one type of proton and this is another type of proton, because the first type of proton is attached to the CH but second type of proton is attached to the CCl. which are having the different linkage, so they are chemically not equivalent. So the first type of proton can be indicated by letter A and second type of proton can be indicated by letter B. Then what about the third type of proton here? This third type of proton is chemically equivalent. It is again attached to the CH, just like the A, but it is not magnetically equivalent. Here you can observe that the proton indicated by A is trans to the chlorine, but this proton is cis to the chlorine. That means even it is connected in a similar way, but it is arranged in a different way. Because of the geometrical isomerism, here the proton indicated by A is trans to the chlorine, but the second type of proton is cis to the chlorine. Now this proton is chemically equivalent but magnetically not equivalent. So according to the rule 1, all magnetically equivalent nuclei will give one NMR signal. But here this proton is chemically equivalent but not magnetically equivalent, so it will give a different NMR signal. So this can be indicated by letter A prime. So it will have a chemical shift which is nearer to the chemical shift of the proton A. So that's why we are indicating the letter A prime. That means A and A prime are having the similar chemical shifts but not the identical chemical shifts, because they are chemically equivalent but magnetically not equivalent. So in this way, in a structure we have to identify first of all chemical equivalent, and if it is chemically equivalent then we have to identify whether it is magnetically equivalent or not. So we can conclude that if two nuclei are magnetically equivalent, they will be chemically equivalent. But if two nuclei are chemically equivalent, they may not be magnetically equivalent. So magical equivalence may or may not be present when they are chemically equivalent. So in order to understand well, let us take one example for the rule 1. So this is one of the structure here, and here we can observe the CH3. CH3 is indicated by letter A, and we can also observe another type of CH3 here, whether both are chemically equivalent or not. So here the CH3 indicated by letter A is attached to CH2, but here the CH3 is attached to CH. That means they are not chemically equivalent because they are having a different linkage. Therefore, they are magnetically also not equivalent. We can indicate this proton as B. And this CH3 is equivalent to the proton B. So again we can indicate by letter B. Now let us come to the CH2 here. So here CH2, which is not equivalent to the CH3 and CH, so it is completely different. So it is another type of proton which is having the different linkage. And finally CH, which is also having the different linkage, so it is indicated by letter D. So here we can observe 4 types of different protons which are chemically not equivalent as well as magnetically not equivalent. So this structure will give the 4 NMR signals. Let us go with another example. So here this is one of the structure here. So this is a CH3. Let us indicate these protons by A. Now here we can also identify another CH3, whether both are equivalent or not. In the first case, the CH3 is attached to the CHCl, but in the second case, this CH3 is attached to the CHBr. So this CH3 is not equivalent, so we can indicate this by letter B. So both of the CH3s are chemically not equivalent, so they will give the different NMR signals. And what about the CH? Here one CH we can observe, and here another CH. Again here this CH is attached to the chlorine, but here this CH is attached to the bromine. So again they are chemically not equivalent. So let us indicate these protons by C, and this is D. Both are different. And finally, what about this CH2? This is CH2 and this is another CH2, whether both are equivalent or not. So this CH2 is attached to the CHCl CH3, but this CH2 is attached to the CHBr CH3. That means again they are having the different environment and different linkage, so they are again not chemically equivalent and they will give the different NMR signals. So this CH2 can be indicated by letter E and this CH2 can be indicated by letter F. So here all the protons are not equivalent, so this structure will give the 6 NMR signals. In this way, according to the rule 1, we have to identify all the chemically equivalent nuclei, and if they are chemically equivalent, then we have to identify whether they are magnetically equivalent or not. And here all the magnetically equivalent nuclei will give one NMR signal.